Neural networks can write code, they can translate languages, generate images, and power the chatbots you've probably been talking to recently. At that scale, they start to feel less like a tool and more like magic. Let me ruin that magic for you, because underneath all of it is an idea that's so simple, you probably know most of it. By the end of this video, a neural network is going to feel less like sorcery and more like something you could have invented yourself. Here's the whole thing in one sentence. A neural network is a function. You feed it an input, it gives you an output. Show it a photo, it outputs cat. Show it a customer, it outputs likely to churn. Regular machine learning does this with one equation. A neural network does something sneakier. It stacks many small computations in layers and squeezes a curvy, nonlinear function between each one. Early layers learn simple patterns. Later layers combine those into more useful ones. That stacking is the entire secret. Let's zoom all the way into the smallest piece, a single neuron. Despite the brainy name, it's just a tiny math function. It does two things. Step one, it takes your input features and computes a weighted sum. Each input gets multiplied by a weight, which is a number that says, how much does this feature matter? Then we add them all up, plus a little offset called the bias, and we call that sum z. Step two, it passes that sum z through an activation function, a function that bends the result into something nonlinear. Call that output A. And that's it. A weighted sum first, and then a nonlinear squish. That's a neuron. If this feels familiar to you, that's great. Take one neuron and make its activation function the sigmoid, which is that classic S-shaped curve that squishes any number into a value between 0 and 1. And congratulations, you've just rebuilt logistic regression. So a neural network isn't some alien from another planet. It starts from the exact same linear score you've seen before. It just builds more structure on top. One neuron with a sigmoid, that's a logistic regression. Many neurons stacked in layers, that's a neural network. Now, the original neuron, which is the perceptron invented back in the 1950s, was exciting because it could learn a decision boundary on its own. But it had a fatal flaw. A single perceptron can only separate things with a straight line. Here's the problem that broke it. It's called XOR, or exclusive OR. The rule is simple. Output 1 when the two inputs are different, and 0 when they're the same. Let's plot those 4 points, and try to draw one straight line that puts the ones on one side and zeros on the other side. You can't. Go ahead and try every angle. There's no single line. And that's exactly where a hidden layer saves the day. Because hidden layers let the network bend and reshape the input space before it makes the final call. They don't just draw a better line, they redraw the whole map so a line becomes possible. So we've established that we need more than one neuron. A layer is just a group of neurons working in parallel, each with its own weights, all looking at the same input. Mathematically, we bundle their weights into a matrix, so the whole layer becomes one tidy equation. A network usually has 3 kinds of layers. The input layer is just your raw features. It doesn't really compute anything, just hands the data off. The hidden layers are in the middle, and that's where all the magic happens. They learn internal patterns we've never explicitly programmed. And then finally, the output layer, which produces the final answer. In a churn model, for example, a hidden unit might quietly learn a combination like low usage and a recent support ticket. Nobody told it to look for that. It just found a useful pattern on its own. Now here's the part most explanations skip, but I think it's one of the most important ideas in this whole video. Why do we even need activation functions? Why not just stack plain linear layers? Let's find out. If we take two linear layers, one feeding into the other, substitute the first into the second, watch what happens. The whole thing simplifies down to a single linear layer. 2 became 1, 10 would become 1. 1,000 stacked linear layers collapse into one boring line. The activation function is what stops the collapse. That little nonlinear squish between layers is what lets the neural network fold and carve up space in complicated ways. Without it, depth is pointless. With it, you get the power of deep learning. That's why activation functions aren't a footnote. They're the reason neural networks are neural networks. So which squish do you use? There are 3 that you'll meet constantly. First is the sigmoid, which is the S-curve that outputs between 0 and 1. It's great for the final layer of a binary classifier, but people stopped using it inside the network because for very large or very small inputs, it flattens out. And a flat curve has almost no slope, which means almost no signal for learning. That's the dreaded vanishing gradient, which we'll talk about in another video. Second is tanh. Similar shape, but centered on 0, which tends to train a bit nicer, but still flattens at the extremes. The third, and the modern default, is ReLU. The name sounds scary. The rule is hilariously simple. If the number's negative, output 0. If it's positive, the output is unchanged. That's the whole function. It's cheap, it trains well, and it's the go-to for most hidden layers today. Its only quirk? A neuron could sometimes get stuck outputting 0 forever. That's what we call a dead neuron, which is why variants like leaky ReLU and GeLU exist. The last layer's job depends on what you're predicting and comes paired with a loss function, which is just a number that measures how wrong the network currently is. Bigger loss equals more wrong. Training is the act of shrinking that number. 3 common setups are if you're predicting a number, like a price, use a plain linear output and mean squared error as your loss function. Predicting yes or no, 1 sigmoid output and a binary cross-entropy loss function will do just fine. Predicting one of the several classes, like cat, dog, or bird, use softmax, which turns raw scores into probabilities that all add up to 100%. And you would pair that with categorical cross-entropy as your loss function. The pattern is the same every time. A loss that's small when you're right and large when you're confidently wrong. That gap is the thing we're about to push downhill. Putting it together, making a prediction is called forward propagation. Data just flows forward layer by layer, no loops. Input becomes the first hidden representation. That becomes the second, and that becomes the prediction. That's why these are called feed-forward networks. Let's do one tiny real calculation so it's concrete. 2 inputs, 2 and 3. The neuron's weights are 0.5 and -1 with a bias of 1. The weighted sum would be 0.5 times 2 is 1, minus 1, times 3, which is minus 3, plus a bias of 1. The total gives us minus 1. Now apply ReLU. The number is negative, so the output is 0. That's it. That's one neuron firing. A real network just does this thousands of times across many neurons and layers, with the weights learned from the data instead of made up just like I did. Okay, prediction done. But a fresh network is terrible. Its weights start out random. So how does it get good? This is the heart of the whole thing. Training means finding the weights that make the loss as small as possible. Imagine the loss as a landscape of hills and valleys, and the network is standing somewhere on it in the fog. We want to reach the very bottom of a valley, so we feel around which direction is downhill. Then we take a small step that way. Do that over and over, and we descend. That's called gradient descent. And the gradient is just a fancy word for which way is downhill and how steep. But a big network has millions of weights. How do we figure out the downhill direction for every single one efficiently? That's the job of backpropagation. And despite its reputation, it's just one idea, the chain rule from calculus, applied very cleverly. Think of it as assigning blame. The loss depends on the final prediction. The prediction depends on the last layer. The last layer depends on the one before it, and so on, all the way back. Backpropagation starts at the error and works backwards through that chain, figuring out how much each weight contributed to the mistake. Forward pass to predict, backward pass to assign blame. Then the optimizer nudges every weight a little in its downhill direction. Predict, measure, send the error backwards, update, repeat. That's the leap that turns random numbers into intelligence. A couple of practical knobs. First, we usually don't compute the downhill direction on the entire training dataset at once. That's too slow. We use mini batches, say 32 or 64 examples at a time. This is faster, and the little bit of noise it adds actually helps the network avoid getting stuck. One full pass through all the data is called an epic. Second, smarter optimizers. Momentum gives the ball inertia. If it's been rolling one way, it keeps rolling, powering through the flat spots. Atom combines momentum with automatically adjusting the step size per weight, and it works so well out of the box, it's most people's default. And the single most important dial, the learning rate, how big each downhill step is. Too big, and you overshoot the valley and bounce around, or blow up entirely. Too small, and the training crawls and may never get there. Get it right, and the loss slides down smoothly. Honestly, a good learning rate matters more than most fancy architecture tweaks. Now, a warning. Because networks have so many parameters, they're powerful enough to memorize the training data instead of learning the real pattern. Like a student who memorizes the answer key instead of understanding the subject, they ace practice and bomb the real exam. The telltale sign: training accuracy keeps climbing, but performance on fresh, unseen data starts getting worse. That divergence is overfitting, and we fight it with regularization. The simplest tool is early stopping. Just watch the validation score and quit training the moment it stops improving. Weight decay gently penalizes huge weights, keeping the model simpler. And dropout is a clever trick. During training, randomly switch off some neurons on each step, so the network can't learn too hard on any simple one. It's forced to learn patterns that are robust. Then at prediction time, you switch everyone back on. One last dose of honesty, because it really matters. Neural networks are powerful, but they are not always the right tool. On ordinary spreadsheet-style data, which are just rows and columns, simpler models called gradient boosted trees are often just as good or better, with far less fuss. A neural network really earns its keep when you have lots of data, genuinely complex interactions, or messy unstructured data like text, images, or audio. It also shines when you can use embeddings to handle things like thousands of product IDs. So a badly trained neural network can absolutely lose to plain old logistic regression. That's not a failure of the idea. It's a reminder that complexity isn't free. Always start simple and make the neural network earn its place. So let's zoom back out. A neuron is a weighted sum plus an activation. A layer is many neurons in parallel. A multi-layer perceptron stacks those layers. Forward propagation makes a prediction. Backpropagation sends the error backwards, and the optimizer updates the weights. over and over until the loss shrinks. But if you remember just one thing from this video, make it this. Neural networks learn representations, not just predictions. Hidden layers quietly transform raw inputs into better and better internal features until the final answer becomes easy. That's the leap that separates them from a plain straight line. And here's the payoff. Everything bigger, the image generators, language models, translators from the start of the video, it's all built on this exact loop. The architectures get more specialized and the scale gets enormous, but the heartbeat never changes. Make a prediction, measure the error, send it backwards, update, repeat. It was never magic. It was just stacked math. And now you know how it works. If this clicked for you, the deep dives on backpropagation and transformers are coming next. I'll see you there.